So here's another example. All right, so in this case, we want to set up and evaluate an integral to compute the length of the curve y equals x to the 3 halves from 0 to 4/3. All right, so remember our formula, right? Our formula for arc length is well, we're taking the integral from a to b of 1 plus f prime of x squared, right, dx. Right, so we have a curve. So now the first thing we need is that we need the derivative of this curve. So I'm just going to do dy dx, same as f prime dx. We're going to end up with 3 halves x to the 1/2. Okay, so there's our derivative, and now we just need to plug it into our formula. So we have the integral from 0 to 4/3, right, because that's the interval we want to find the arc length over, and then we have the square root of 1 plus this f prime squared. So we're going to have 9/4, and then the square of the square root is just x. All right, so that's nice. Doesn't look too bad to integrate. Some of these are not easy to integrate. In fact, it's actually hard to find a problem that is easy to integrate. So I'll tell you more about that in a minute. All right, so this looks like a pretty straightforward substitution, a simple substitution problem. So I'm going to let w equal 1 plus 9/4 x, and so that means that dw is equal to 9/4 dx. Okay, but we don't have 9, we need just dx, so we get 4/9 dw is equal to dx. Okay, so that's we can substitute 4/9 dw for dx. Now, since this is a definite integral, I can also transform the limits of integration. So at the bottom end of the interval, I've got x equals 0. So what is w when x equals 0? So I can just plug x equals 0, and I'll get w equals 1. And then the other limit is that's supposed to be 4/3, not 4/2. 4/3. So when x is equal to 4/3, I plug that in, 4/3 times 9/4, right? That gives me 3 plus 1, so w equals 4. All right, so now I can actually just integrate this in terms of w, and I don't have to go back to x because I've also transformed the limits of integration. So I'm going to integrate now from 1 to 4 the square root of w dw. Whoops, not dw, is it? it's 4/9 dw, right? Dx is 4/9 dw, so whoops, and 4/9 dw. All right, so I'm going to pull the 4/9 out front, and the square root, if I integrate the square root of w, what I end up with is 2/3 w to the 3 halves. And I'm going to evaluate that from 1 to 4. All right, well, I can combine the 4/9 and the 2/3, so I'm going to get 8/27. And then I have 4 to the 3 halves, and then I'm going to have minus 1 to the 3 halves. Okay, 1 to the 3 halves is just 1. The square root of 4 is 2, and then I'm going to cube it, so this becomes 8. So it becomes 8/27, and then I have 8 minus 1, which is 7. 7 times 8 is 56, so I get 56/27. And I can't reduce that. That's 7 times 8, and then 27 is 3 times 3 times 3. No common factors. So that is my final exact answer. If I want the exact answer, that's it. So, all right. So that takes care of our discussion of arc length for just regular functions. We're also going to look at the arc length for a parametric curve. So that's what we're going to do next.